is Brad Grzesiak, and I am CEO of BendyWorks. Today I'm going to tell you a few ways to simplify your challenging software problems using rocket science, of all things. You can find me on the internets as Listrophy pretty much everywhere. I'm going to start off by saying, showing a quote from my friend Ash, who said, "Whenever Brad is drinking, you want to make sure you're sitting next to him because instead of being obnoxious, he teaches you orbital mechanics." The thing Ash doesn't know is that you don't actually have to feed me beer to do that. So after my talk, at any time during the conference, if you want to learn all about rocket science, feel free to ask me. Just a quick note for anyone who has visual issues. There's going to be one animated GIF. It's pretty mild, though, so hopefully it won't cause any issues. Today's agenda consists of three things. I'm going to teach you how we in the aerospace industry reduce cognitive load. We're going to see how to visualize simulations with graphics, and we're going to control and respond to real-world processes. I actually worked for an aerospace company for a bit over 5 years, and during that time, nothing I worked on ever went to space. And then 5 years after I left that company, something that I worked on finally went to space. So I do have some basis here. So let's begin. Reducing cognitive load. So the thing to learn is that us rocket scientists, we're not actual superheroes. We just went through a path during school that taught us bit by bit towards what we needed to learn. Just like you in your programming career have done the same. So we just learned tricks and techniques to tackle this really difficult problem. So one of the main ways that we do that is we use higher levels of abstraction, if that sounds familiar at all to you. So in programming, what we'll typically use for dealing with things that are engineering-like or graphics-like, so we'll use primitives, x, y, z for position. If we need to find the magnitude of a vector, we'll use square root, Pythagoras theorem. If we need to add two positions together, we might use a zip plus a map. We've got this matrix times a vector. And when it comes to rocket science, we've solved this. Mathematics has solved this. And so instead, what we use is matrices and vectors. So you can see, you can just call that magnitude. This is built into the Ruby standard library, if you require the right library. And on that third line, you can see vector 1 plus vector 2. If you use just regular Ruby arrays, that'll just concatenate them. So instead of having a 3-element array, you now have 6, and that's completely useless if you're trying to add vectors. And similarly, that last line, if you're trying to multiply a matrix times a vector, it's really hard with just standard Ruby, but if you use the right libraries, you can do it just times that. You might be thinking to yourself, holy crap, matrix times vector? Don't worry too much about this. The interesting thing about these three words is that the word times is actually the most complicated term in these three, just because it's an overloaded term in mathematics. Vector is just basically an array, and matrix is an array of arrays, is really what it comes down to. So let's talk about why we would ever want to use matrices and vectors in computer science problems. They're primarily used for a thing called linear transformations. And we see these frequently, but they're simplified for us to be more easily accessible to us as programmers. So in CSS3, for example, you have the transform key, and you can apply scale, rotate, skew, all these things. And these, under the covers, it's actually just using matrix times a vector to do these things. And when it comes to rocket science, we frequently use this in kinematics and kinetics. So let's look at that. Matrix times a vector. This is basically how it works. I'm also going to be showing 2-element vectors and matrices instead of 3, just on a plane because it's easier to understand. Typically we would use 3. So the way I remember how to manually do a matrix times a vector is take the vector, just rotate it up on top, and then kind of pass through multiplication and vector and addition as you go through the matrix. So it's really that simple. Fortunately, we use higher levels of abstraction, so we never actually have to implement this. If you were trying to do this from scratch in Ruby, you might implement it on the left. Whereas the standard library actually has a library called matrix, and you can just pull it in. And matrix actually includes both matrix and vector. So you can use both of them through that. And so the nice thing is you don't actually have to have a matrix times vector method because you can literally just multiply them together. And the nice thing is this takes care of dimensions for you. So if you have dimensions that don't match up and you try to multiply them, your solution on the left might accidentally multiply them together and not raise an error, whereas on the right, it will tell you, oops, you made a mistake. So one example of a linear transformation is the rotation matrix. It looks as simple as this. It's got a little bit of trigonometry in there, but again, you don't actually have to implement this. It's already built in. So if you take the rotation matrix and you set theta, I want to rotate something 30 degrees, times a vector of 1, 0, that just turns it into about 0.87 and 5, and you can see the results of if you have a 90-degree one. So basically all it is if you want to have a rotation of 30 degrees, and you treat an image as just a very long vector, it just kind of works like that. So that's how we reduce cognitive load, just by using the tools that mathematics has given us and having a higher level abstraction. So it's something that you can use, especially in graphics. Whenever you're transforming something that is in the domain of the real world and you want to simulate it on a screen, you can use a linear transformation to do that using matrices and vectors. So moving on, we're going to talk about exactly that, visualizing simulations with graphics. So why would we ever do this? Well, the four main reasons that I can think of, the reason that I used it back in my heyday as an aerospace engineer is I was dealing with complex systems. There was a high sensitivity to the inputs. So if you change one thing a little bit, if you think of like a screw hole being really close to the edge of a plate, if you move it just a little bit too close to the edge, the whole thing fails. So you have a high sensitivity to the inputs of how close that hole is to the edge. Frequently, there's this requirement for pattern recognition that computers are actually terrible at and humans are really, really good at. So that's part of it as well. And then typically what we're looking for is just good enough. It doesn't have to be the perfect solution, but it should be good enough. The thing shouldn't fail, basically. And the way you can translate this to your experiences as a software engineer is, if we take out those last two requirements and we replace the word simulations with tests, that's basically what we're doing when we're testing. We have this very complex system that is our software, and it has a high sensitivity. If you make one mistake in your code, your tests will fail, and that's going from green to red. And so you have this really, really high sensitivity. And so it's similar in one respect to using graphical simulations. So in aerospace engineering, I used graphical simulations to implement all these things. So when you're launching something into space, it endures a lot of different frequencies at a lot of different magnitudes. So the engine is making a lot of noise that reverberates through the entire structure. As you go faster and faster within the atmosphere, you start experiencing max Q, which is max Q is the point where you have the most aerodynamic load, and that kind of shakes the whole thing. And so you're experiencing all these various vibrations. And the rocket designers have actually come up with spectra of, if you put something on a rocket, this is what you can expect to feel. And so that's one example of a situation where we need to do some simulations. Also, kick tests in zero gravity, you're not standing, and so you could easily, as an astronaut, accidentally kick the front face of a thing. There's the thermal equilibrium problem. This is actually solved by NASA early on when you have satellites that one side is typically facing the sun, the other side is facing away. Heat pipes were actually first used in a significant manner by NASA to make sure that the heat coming from the sun actually gets radiated out to the back. So you can thank the technology in your laptops, you can thank NASA for that one. And then designing to a safety factor. Again, making sure that if the safety factor is determined to be about 1.5, we want to make sure that we're actually doing that well. And then a final thing is the fun thing to talk about, which is n-body orbital mechanics. Basically, what happens when you throw a bunch of bodies into space that interact with each other in gravity? So we're going to talk about that. So the n-body problem is governed by a few simple things. You have Newton's 3 laws, you really only use 2 of them, and gravity as well. And it's basically solved for n equals 2. There are closed form solutions to that, but once you get beyond 2 bodies, unless you have very specific assumptions applied, there's actually no closed form solution to these problems. There's no periodic motion that happens. And very, 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 very smart mathematicians have determined that this is true. So we can kind of assume that it is. So here are the 5 things that we're gonna use in order to evaluate the n-body problem. We have the top, force of gravity. So this is the normal thing that you may have learned in middle school or high school physics. We have the second law, which is force equals mass times acceleration. We have Newton's third law, which is for every force, there's an equal and opposite reaction. We have velocity and acceleration. It's just that the derivative of velocity with respect to time is equal to the acceleration, and similarly for position and velocity. Everything that you see on the screen here, if it's bolded on the right, that means it's a vector instead of just a number, right? So mass, it's just a number, but acceleration, you have a direction that you're going, as well as a magnitude. So let's simplify this into ways that we can understand it. First of all, let's pay attention to those last 2 lines. We're talking about derivatives. We're talking about calculus, and I know that everyone in the room is not all excited about calculus as much as I am. So this is the formal definition of a derivative. You may have experienced it in your calculus class. This is neat, but it's kind of annoying to actually deal with in the real world. So what we're actually going to do is, instead of having delta t, which is the difference in time, instead of it approaching 0, we're just going to say, let's just set it to something really small and say that's good enough, basically. And I left the units off, and so you can think of like maybe it's going to be a nanosecond in one situation, or a millennium if you're talking about how the galaxy spins or whatever. And so we're just going to use that. And now what we can do is we can just translate those derivatives into this one equation below. The acceleration now is just the difference in the velocities divided by the time difference. And now that bottom line, I think, makes a lot more sense. So you can say the velocity that I'm going right now is equal to the velocity that I had a millisecond ago plus the impact of acceleration on that velocity. So that's one way to think about it. And now we can apply that same thing to position. And now we have, instead of these last 2 lines, we can say, well, that's pretty simple. And now our most complicated thing in this entire equation is division, which is, I think, something that a lot of us can handle. So we're just going to swap around acceleration with force and mass and use some notation. And so now we have, at the top, we have r, which is our distance between 2 bodies. And that can give us a force that they have now. We can take the force that they have now, divide it by the mass. We get an acceleration. We can take acceleration and take the previous velocity, get a current velocity. We can take the previous velocity and, or the current velocity and the previous position and get the new position. So now we have a way to move things, basically, just due to gravity. So this is what it looks like in Ruby. That's all it is. It's a little dense, but it's easily understandable. And that second line right there, gravity, you might say like, well, that's kind of complicated. I don't, it's just one equation. So that's really all it is. You're just, summing all the forces from all the other bodies and applying that force to one body. And then you loop over each of your bodies to do that. So that's all it is. So I'm going to show a demo of this. And using Ruby, specifically Ruby shoes, we can show how to actually do that. If Keynote will go out, there we go. So what I'm going to simulate here is the sun, and we have at the bottom, we have Jupiter. And at the top, we have, let's say, a comet. And one of the things that you may have learned is that because of some of the larger gas giants, we don't have as many detritus in our solar system because they ejected. And this isn't a simulation of what's actually going to happen. So the circles aren't actually to scale, so you're going to see the white go inside the red, and that's just showing that it's getting really, really close. And it's actually going to slow down a bit once it gets closer to Jupiter, because I'm actually going to reduce the delta time just so that I can get a more accurate representation of that. So here it's going, it's just in a regular elliptical orbit, and when it's going to encounter Jupiter, if everything goes correctly, that I've tested many, many times, live demos. So now it's slowing down because I'm using a slower delta time. And it's going. And now you can see it's actually getting ejected from the solar system. So that's actually what's happening in our solar system. Jupiter, Saturn, et cetera, are basically flying really close to these comets, and the comets basically get ejected, just from these simple equations that we identified. And Jupiter continues on its way almost completely unaffected. So that's simulation with graphics. So now we're going to talk about controlling and responding to real-world processes. So the world is super complicated. In some of your classes that you might have had in physics, you might assume that there's no air resistance, frictionless surface, et cetera, et cetera, et cetera. The problem is, in the real world, you can't actually assume that these things don't affect you. And so you can't specify a solution a priori if you're in the real world. It will get affected by all these little things like air resistance and friction. So, as my friend Helmuth von Moltke the Elder said, no battle plan ever survives contact with the enemy. And so all these little perturbations are going to severely affect a solution that you try to come up with ahead of time. So the answer to this problem is just react to the situation. Instead of trying to get the exact answer ahead of time, just react to what's happening to you. And this is not React.js, it's just react to the real world. So again, in aerospace engineering, we have this thing we call the feedback controller. And what we have is, we start with a desired output, we implement a controller, the controller turns that desired output into a control, that controls the thing does its thing, and you get an output. And then what you do is you take that output, and then you feed that back into the controller, feedback. And you usually do that via sensors. And so one example would be, if you're Aaron Patterson, you might want to cure your meat. And so you want to set a desired humidity for your cure. You write some Ruby that turns that desired output into should I turn the dehumidifier on or off? That changes the humidity inside of the cure, result in a humidity percentage. Then you have sensors that detect what the humidity is and feed that back into the Ruby. Or if you're more into rocket science, you can apply that to a fucking rocket. So the input that you have for a rocket is actually just thrust percent, like how much thrust should I be applying right now? And if you want to say hover a rocket, not that you would actually want to do that, but if you wanted to, you could say, like, I want to actually hover it at a specific altitude. And what percentage thrust should I use? It's actually a very complicated problem, especially if you consider that the mass of the rocket is going to be decreasing as you shoot fuel out the business end of the rocket. So it's actually a nonlinear second-order differential equation. Kind of complicated to deal with, and we're not taking into account air resistance, et cetera, if you're trying to come up with a solution ahead of time. So instead, what we use is a PID controller. And PID stands for proportional, integral, and derivative. So we take this controller, and we look at the difference between what we're sensing as the output and the desired output, and we call that just the error. And so we take that error and we say, all right, that's a proportional term. All right? So the next one that we look at is the derivative term. We just take that error, subtract the previous error, divide by time. Again, this is simplified derivative. And then integral, we just kind of accumulate the error that we had since we turned the thing on. So we just take the previous integral and then add the error times the time. And then you just multiply it by some constants that you can either spend a master's degree figuring out how to appropriately come up with these the first time, or you can just trial by error it. And so at the bottom, you can see I'm setting the thrust, 0.1 times the proportional value, 0.003 times the integral value, and then 0.08 times the derivative value. You can just kind of play around with it until you get to it. But that's all it is. And you're just sleeping every 0.2 seconds to get that. So let's do another demo. How many of you ever played Kerbal Space Program? Yeah, so we're going to use that. So here we have it. Apologies, it's a little small. The things to note are up here we have the altitude, is 79 meters, and then down here we have the throttle. So up here is like 100%, and down here is 0%. And so I wrote some Ruby that you mostly saw on the screen already to actually do this. So I'm going to run that Ruby, and it just uses a library to connect to Kerbal Space Program to control my thing. So we have a countdown, 3, 2, 1, go. So you can see it's taking off. I'm not doing anything, hands are up here. And it shut off the engine because it got a little too high, and it's come down, and it turns it back on, full throttle, and then it's gonna kind of get back to 150 or so, and then turn it on. And that's all it is. The most complicated thing I did in this program is division, and it's handling all this. And one of the cool things is once it really settles down, if I were to turn off this controlling Ruby, the thing would actually start rising. And the reason is what I said earlier, is that the mass is getting less. And if you just set the throttle at one value, as the mass goes down, the acceleration goes up. So 149, that's pretty close. It'll get to 150 eventually. And so there it is. And so we can actually turn that off and watch it climb. Because it's not feathering the throttle down anymore. So you can see it starting to go up. So that's that. Thank you. And that code, I believe, is up on GitLab, so I'll share that via Twitter. So that was all I have for today. 3 ways that you can use concepts used in aerospace engineering and rocket science to help simplify the things that you're doing. You might encounter a really gnarly problem, and it might just be that rocket scientists have already simplified this for you, so you can look into that. So here are my photo credits, and thank you for your time and attention.